In this video, we are going to look at properties of exponential functions. First, we will look at exponential growth, and then we will look at exponential decay. So to start off, let's look at the function y equals 2 to the exponent x. We will graph this function. By doing that, we will first make a table of values, starting from x is -4, going up to x is +4. So to do that, I'm going to substitute in each value of x into the exponents. So 2 to the -4, and so on. So now we will evaluate each of these using the exponent rules. So remember that when you have a negative exponent, you take the reciprocal of the base. In this case, it's 1/2. And then the exponent becomes positive. So it's 1/2 to the exponent 4. So 1 to the exponent 4 is 1, and 2 to the exponent 4 is 16. So the next would be the reciprocal, which is 1/2 to the exponent +3, which is 1/8. The next would be 1/2 to exponent +2, which is 1/4. The next would be 1/2 to the exponent +1, which is 1/2. The next 2 to the exponent 0 is 1. 2 to the exponent 1 is 2. And then 4, 8, and 16. So this is more than enough points to see the general shape of the graph. So I'm first going to plot when x is -4. I have a y value of 1/16, which is very close to 0, but not quite 0. And then when x is -3, I get 1/8. When x is -2, I have a quarter. And then when x is -1, I have a half. And then when x is 0, I have 1. And then I have 2. And then 4. And then 8, and then 16. So now I will join these points together. And label the equation, y equals 2 to the exponent x. So what you notice is at the beginning, you start really small. You have a y value of 1/16, and 1/8, which is still pretty small, and then 1/4, and then 1/2. And then you start noticing that we're rising really quickly because each time we're doubling. So we're at 1, and then 2, and then 4, and then it keeps going up faster and faster and faster. On the left, when the x values are negative, you notice that the y values are all fractions. They're very small, and they're close to 0. They don't actually ever reach 0. Even as x gets more and more negative, it's impossible for the y value to be 0. So what we say is it approaches the x-axis on the left, so that means that the x-axis is actually an asymptote. So I can draw that here and label that as y equals 0. So the exponential function has a horizontal asymptote, but it does not have a vertical asymptote because as x gets larger and larger, the graph moves up and to the right. There's nothing stopping it from moving to the right, although it moves up quicker than it moves to the right because it's growing exponentially, but it does not have a vertical asymptote. So some features that you need to recognize. Discuss the general shape of the graph. As you move from left to right, the graph starts slowly and then it grows very fast. So looking at the intercepts, the y-intercept, there is one here at 0, 1. An x-intercept, there are no x-intercepts because that is where the asymptote is. Now this is just for a general exponential function. This is without any transformations, as the x and y intercepts could change based on the transformations. And then the domain and range. So the domain, the graph can continue to the left and it can continue going to the right. So the domain x is an element of all real numbers. And the range, y is an element of all real numbers, but y has to be always greater than 0. It cannot be equal to 0, it's just greater than 0. So to discuss the behavior as the curve approaches the x-axis, we can look at the graph and we notice that as the curve approaches the x-axis, which is here on the left, it gets really close to the x-axis, but it does not touch or cross the x-axis. And we already talked about that's where the horizontal asymptote is. So there's an asymptote at y equals 0. And finally, when we are asked to describe the behavior of the curve, this could also be asked to describe the end behavior. So what that means is what happens when x approaches negative infinity. So as x gets smaller and smaller, and what happens as x gets bigger and bigger as it approaches positive infinity. So let's go back up to the graph. And as x gets smaller and smaller as it approaches negative infinity, the y values get closer and closer to 0. And as x gets bigger and bigger, as it reaches positive infinity, the y values get very big as well. So they also approach positive infinity. So how we write that in mathematical notation, we say as x approaches negative infinity, y approaches 0. And as x approaches positive infinity, y approaches positive infinity. So this is how we write it using mathematical notation with the arrows. The arrow just means approaches. So using words, we would say as x approaches negative infinity, y approaches 0. And in part B, as x approaches positive infinity, y approaches positive infinity. So I've just written that here for you in words. So we just looked at exponential growth, specifically the function y equals 2 to the x. So there the base was 2. So anytime the base is greater than 1, it will be an exponential growth. Now let's look at exponential decay. So decay will happen when the base is between 0 and 1. So it has to be less than 1, but we only ever look at when the base is positive. So here, because I have a base half, I know that this is going to be decay. So again, I chose x values between -4 and 4. And now I'm going to find the corresponding y values. So I substituted in all the x values for my exponents. And now I'm going to evaluate. So the first one is 1/2 to the exponent -4. The negative exponent says to flip the base, so that's 2 over 1. Or I rather write it as simply 2 to now the positive exponent of 4. 2 to the 4 is 16. Next, take the reciprocal of 1/2, which is 2, to the exponent 3, which is 8. Next, I'm going to change that to 2 squared, 4. Next, 2 to the exponent 1, which is 2. Next, 1/2 to the exponent 0 is 1. 1/2 to the exponent 1 is 1/2. 1/2 to the exponent 2 is 1/4. 1/2 to the exponent 3 is 1 over 8. And 1/2 to the exponent 4 is 1 over 16. So now I can plot these points. So the first point is at -4, positive 16. And then -3, positive 8. And then -2, positive 4. And then -1, positive 2. And then 0, 1. And then 1, and I have a y value of 1/2. And then when x is 2, I have a y value of 1/4. And then I get a y value of 1/8, and then a y value of 1/16. So again, try not to cross the x-axis because that's our asymptote. So we get really close to it, but we're not going to cross it. And then we'll just draw our curve through the points and then label the equation. And just like in the other graph of exponential growth, we have a horizontal asymptote at the x-axis, so the equation is y equals 0. So again, let's talk about the features. So the general shape of the graph, at first it decreases quickly and then very slowly as you move from left to right. Looking at the intercepts, again, we have a y-intercept at 0, 1, just like we did for exponential growth. And the x-intercept, there are none, again, just like it was for exponential growth. Looking at the domain and range, they are the same as they were for exponential growth. X is an element of all real numbers, and y is an element of all real numbers, but y must be greater than 1. And again, you can see the graph can move to the right, and it can move to the left. So there's no restrictions in the domain. But in the range, looking up or down, it can move up, but we have this asymptote stopping it from moving down below the x-axis, so that's why y has to be greater than 0. And then to discuss the behavior as the curve approaches the x-axis, again, as the curve approaches the x-axis, it gets very close to it, but does not touch or cross it. So I've written that here, and remember that means there is an asymptote at y equals 0. So that's a horizontal asymptote. So to discuss the end behavior, as x approaches negative infinity and as x approaches positive infinity, let's again look at the graph. So as x approaches negative infinity, meaning as it moves to the left, we see that y approaches positive infinity, and as x approaches positive infinity, saying it's moving to the right, y is approaching 0. So I've written that here, first mathematical notation, and then using words. As x approaches negative infinity, y approaches positive infinity, and as x approaches positive infinity, y approaches 0. And finally, we will take a couple of minutes just to compare the similarities and differences of the two functions that we've looked at, exponential growth and exponential decay. So similarities, we notice that they both had the same y-intercept at 0, 1. We also notice that they have the same asymptote of y equals 0. And the differences, we notice that the end behavior is opposite. And you should have also noticed that the shape is reflected in the y-axis. So let's revisit the graph just to talk about this last point. So here I have the first graph, the exponential growth in green and the exponential decay in blue. And what you do notice is that they are reflected in the y-axis. What you could also notice is if you take the equation for the exponential decay, 1/2 can be written as 2 to the negative 1, and that has the exponent x. And then using the rules of exponents, you can multiply the exponents, so you get negative 1 times x, which is negative x. This negative is actually a b value of negative 1. If you remember transformations, when you have a b value of negative 1, that says there's a reflection in the x-axis. So really a decay is just a transformation, where b is negative 1, of your exponential growth. And just a final note of the expectations of when you are graphing exponential functions. If you're graphing exponential growth, you would want as many points as you could fit on the grid on the right side. So you would want the y-intercept for sure, and then you would have here when y is 2, y is 4, y is 8, and y is 16, because that fits on the grid. On the left side, when you approach the asymptote, you just want the 1 point, because then it gets really squishy. So as long as you have the 1 that shows that you're close to the asymptote, so here when x is negative 1, you have a y value of 1/2. That's fine. And then for decay, again, you want all these points that are far apart on the left side, as long as they fit on your grid. You want the y-intercept, and then just the 1 point that approaches your asymptote is fine. You don't need all of these points, because as you can see, it gets really squishy. And as long as you have 1 point and then the curve shows that you approach the asymptote, you're fine.